So carbonyls are weak electrophiles. To do chemistry on a weak electrophile, we're going to need a strong nucleophile. We've already talked about one type of strong nucleophile, the organometallics. Now we're going to talk about another type of nucleophile, the hydrides. So this video is about the hydride reagents. There are two hydride reagents. One is sodium borohydride, and the other is lithium aluminum hydride. Lithium aluminum hydride is more reactive. But for our purposes right now, when we talk about carbonyls, we're going to use them just about interchangeably. So, what do these reagents do? Well, they're both sources of hydride. Hydride is H-. That's a hydrogen with a lone pair and a negative charge. That's very different from being a proton, H+. Hydrides are electron rich. Because they're electron rich, they have two properties. They can be either bases or they can be nucleophiles. And we're going to focus on the nucleophilic side of our hydride. So how do these get used? Let's say we have a carbonyl. We can react this with a reagent like lithium aluminum hydride. Lithium aluminum hydride, when I write lithium aluminum hydride, it's not obvious to me that that's a source of H-. So I will always explicitly call this out and say that is equivalent to H-. H- now, that tells me electron rich, it's an anion, it is a good nucleophile. So what do strong nucleophiles do to carbonyls? Well, they attack the weakly electrophilic carbonyl. In doing so, we form this anion. This is, again, as we saw before, a tetrahedral intermediate. Hey, you want to be fancy, you can put it in brackets. Optional. And then once we form our tetrahedral intermediate, what do we do to our tetrahedral intermediate? Typically, this won't always be the case, but we treat it with water. We protonate it. We need to neutralize it so that oxygen picks up a hydrogen off of water. And we get an alcohol. So now we're attacking our carbonyl with a nucleophile. That nucleophile tends to be a simple nucleophile. It's just a hydrogen. It's H-, it's a hydride. So it's another way to add something to our carbonyl. Let's see sodium borohydride in action. So one thing you'll note with lithium aluminum hydride, we had to have a second step and add water. Well, like Grignard reagents and like organolithium reagents, lithium aluminum hydride is very reactive, and so we tend to use it with solvents like ether or another solvent like THF. The structure of THF is not that important. The point of THF is it's an aprotic solvent. No alcohols in here, no water. So if we need water, we have to add it in a separate step because there's no water in these reactions. It's just like the organometallic reactions we saw before. Now we could do the same reaction and use sodium borohydride. Sodium borohydride is a little bit different in that sodium borohydride is less reactive. And sodium borohydride will tolerate having an alcohol as a solvent, like ethanol. Now sodium borohydride is still a source of H-. H- attacks. We form this very same tetrahedral intermediate. Like I said, these are almost interchangeable. Now we don't need a second step with sodium borohydride because we have our proton source, ethanol, in the reaction. And so we don't need to add water. We already have a protic solvent, ethanol, and we get to the same place. So they're a little different. Sodium borohydride technically only takes one step in terms of reagents being added instead of two steps needing a separate water step. But they're very similar. So these are the hydride reagents. They are strong nucleophiles and they attack carbonyls.